Okay, so we have our x comma z, this is our z equals 0 plane, and then we have epsilon 1 mu 1 and epsilon 2 mu 2. Okay, so now we are going to do the boundary conditions, okay, at z equals 0. So we can say that the magnetic field, right, the parallel component of the magnetic field has to be continuous, right, because there are no surface currents. Okay, so since Js is 0, we can say that the parallel components, right, parallel to the interface, right, or z equals 0 plane. So we can say the net field on the left side of the boundary, right. So the net field there is going to be the sum total of the fields caused by the incident wave and the reflected wave, right. So we are going to say that Hi plus Hr is equal to Ht. Okay. So since there are no surface currents, we can say that the parallel component of the H field, since all of the magnetic field is parallel to the plane, we can just say the entire vector, right. So entire magnetic field vector on the left side of the boundary, the entire magnetic field vector on the right side of the boundary has to be the same. Okay, so remember that z equals 0, right. So we know the expression, since all of these vectors are in the y direction. Let's just look at the magnitude. Remember Hi, we wrote it as H0, right, Ey cap, and what was the spatial dependence? We said it was e to the minus j kx I x. Remember, e to the minus j k z I z is 1 because z is equal to 0. Okay, and then the reflected field magnetic vector is H0r e to the minus j kx r x. You can always verify your notes, or you can go back into the video and confirm these equations, right. Kxt x, right. So what are we doing here? We are simply setting z equals 0, right. We are just looking at the interface, and this is the continuity equation, right, coming from our Maxwell's boundary conditions, right. So what then is another boundary condition we can invoke? It is the electric field, right, that is also parallel to the boundary. So if I were to look at what is the component of the electric field that is oriented in the x direction, right. So I am getting that to be cos theta I Ex, right. So eta 1 H naught cos theta I e to the minus j kxi x. This is my electric field parallel to z equals 0, or the dielectric boundary, right. That is coming only from the incident beam. Let's not forget that this is not the only source of electric field at the boundary to to the left of the boundary. Let's take a look at ER. I also have a eta 1 H0 R minus cos theta R Ex, right. So, let us write that minus eta 1 H0 R cos theta R e to the minus j kx r x. This is my electric field parallel to z equals 0, right. On the left side. Okay. So, I am just looking at the magnitude of the electric or the electric field vector magnitude that is parallel to the boundary. And what is it for H0t? It should be, by just inspection, eta 2 H0t cos theta t e to the minus j kx t x. Okay. We can also verify this, that the x component has a plus cos theta t. Okay. There are two other boundary conditions also, but hopefully there should be no conflicts, right. There should be no new information. We will notice that we can just use this to sort of make certain conclusions already, right. So, let us see what we can do with these equations. Okay. So, one thing that we can notice, right, if I have to satisfy, let us call this equation 1 and equation 2, right, to satisfy 1 and 2 for all x, right. So, remember that there is a e to the minus j k x form for each of the three components, incident, reflected and the transmitted beam. And if this has to be equal for all x's, right, regardless, then what can I say? Kxi has to be equal to kxr has to be equal to kxt. That is the only way you can match this for any x, right. So, remember that this boundary condition is met all along the boundary, right, whether it is x equals 0, minus 1, plus 1, whatever it is, right. So, what happens when kxi equals kxr equals kxt? The exponentials cancel off, right, so that we do not have to worry about them at all. That is the only way in which we can actually find a reasonable solution for H0r and H0t. Okay. So, this is a very, very important condition. We call this the phase matching condition. Right. So, we need to match the phases. Right. So, remember that kxx plus kyy plus kzz is essentially the phase of the wave, right. Of course, we are disregarding the omega t phase, but assume that omega t is present for all of the field components, right. So, there is of course going to be a e to the j omega t and they will cancel off anyway, right. So, at any instant of time all along the boundary we expect this boundary condition to be satisfied, and if this has to be satisfied, then we notice that there has to be a certain phase matching condition. Okay. So, what can we say? Remember kxi was ki modulus cos theta I, right. So, let us check that. Sorry, kxi was ki sin theta I. which was kr sin theta r, and which is also kt sin of theta t. Okay, but remember ki magnitude is equal to kr magnitude, right? Remember, the modulus of the k vector for a plane wave in a given dielectric medium is the same, right? It is given by the relation omega square root of mu times epsilon of that medium. So, since the incident and reflected waves are in the same medium 1, the modulus of the k vectors has to be the same, right? So, when I take the first two, I essentially get sin theta I is equal to sin theta r, right, or theta I equals theta r. Okay, this is probably something that you already know, right? It's probably taught to you as the law of reflection, that the incident and the reflected angles are the same. Okay, so it's no surprise, but remember that the root, right, or the basis for this claim, now you understand, right, comes from the Maxwell's equations itself directly. Okay, so this is the power of Maxwell's equations, right? We are able to explain all phenomena thereof, right, at whatever complexity you might think of for a subsystem or a system. We are able to use Maxwell's equations in a procedural sense, right, in order to derive more macroscopic observable quantities, right. So, let us try to club the last two equations, right. What is that saying? So, this is equal to omega square root of mu 1 epsilon 1, and the modulus of kt is omega square root of mu 2 epsilon 2, right. So, we can say omega square root of mu 1 epsilon 1 sin theta I is equal to omega square root of mu 2 epsilon 2 sin theta t. Okay, so the omegas cancel, and you can say that square root of mu 1 epsilon 1 sin theta I okay. So, this is the most comprehensive Snell's law, right. So, of course, if you are looking at a non-magnetic medium and say mu 1 is equal to mu 2 is equal to mu naught, so the mu's cancel off, right, and if you define the refractive index as square root of epsilon, right. So, the n here is the refractive index, right. And I am defining that as the square root of the permittivity of the medium, right. If I did that, I basically get the more popular expression okay. So, if I assume that I do not have a magnetic medium and the permeability is just mu naught, then I can simplify it to the more popular Snell's law relationship that relates the refractive indices of the two media and the angles of the incident and reflected waves, right. So, we have done good here, right. Remember that the unknowns were essentially H0r, H0t and theta I and theta r, right, and we have actually found the two thetas. Okay. So, the orientations we have got. Okay. So, this is how much high school taught you, right, but you now know the basis of how Snell's law is derived. Why is Snell's law, how we arrive at the Snell's law, right. You know the derivation, you know how it is related to your Maxwell's equations, right. It essentially comes from a phase matching requirement at the boundary. Okay. So, all that is left is to understand the amplitudes, right, which is new territory. I need to understand what is H0r and H0t. So, remember, assuming that the phase matching condition is kept, we can write equations 1 and 2, right. So, equations 1 and 2 transform to, so we have H0 plus H0r is equal to H0t, okay, because e to the minus j k x I x and all the exponentials, they cancel off, right, from both sides. And from the electric field boundary condition, we get eta 1 H0 cos theta I right. So, we can now incorporate what we know about the angles, right. So, I can say that minus eta 1 H0 r cos theta r, but it is simply cos theta I, right, because theta I and theta r are the same, and this is equal to eta 2 H0 t cos of theta t. Okay. I do not quite have a very nice relation for cos theta t. I know sin theta t. Sin theta t is related to sin theta I, but we will try to incorporate. But it is to be understood that theta t is known, right, at this point. The only unknowns are H0r and H0t. You should be convinced that we should be able to do this now, right. I have two linear equations and two unknowns. Okay. This is the reason also why I did not go for what the other two boundary conditions gave me. Okay. I have enough information with me with these two boundary conditions to actually extract all the unknowns. Okay. But it is also important as students that the other two boundary conditions are not in conflict with any of these solutions. Okay. So, I will leave that as an exercise to an astute listener to actually ensure that he writes down the boundary conditions, the other two, okay, which is to relate the normal components, right. Of course, the magnetic field normal component does not give us really much information. It will just say 0 plus 0 equals 0, because the magnetic field has no component that is normal to the boundary. But nevertheless, you can look at the displacement vector that is normal and ensure that we are not getting any contradictory conditions, right. You should understand that whatever we get from the displacement vector equation also, because there is no surface charges, should actually be in correspondence with what we get from here. Okay. Okay. So, at this point it is important to define a few quantities, new quantities, and we are going to do this particularly because we want to invoke the homomorphism between the plane waves from Maxwell's equations to the voltage and current waves in transmission lines. Okay, let's not forget that there is this intricate relationship, which is the reason why we teach the course this way, right? So in order to invoke that, so that we can actually use the same concepts that we used in transmission lines even for electromagnetic waves interacting with the dielectric media around it and boundaries, we will try to come up with certain key definitions. Okay. So, I am going to write these equations as Hy of the incident wave, right. It only has the y component, but nevertheless it is the y component of the magnetic field of the incident wave plus the y component of the reflected wave is equal to the y component of the transmitted wave, right. So, I can write the first equation as Hyi plus Hyr is equal to Hyt, and the second one is essentially looking at the x component, if you remember. So, Exi plus Exr is equal to Ext. Okay. So, now we will look at the second equation here, and we will define 1 plus Exr by Exi. Remember, Exi is a known quantity, right? That is why I am normalizing my Exr and Ext to Exi, and I will call my reflection coefficient as this ratio and the transmission coefficient T as Ext by Exi. These are each called the field reflection coefficient and the field transmission coefficient. Okay. The emphasis on including field in front of the reflection and transmission coefficient is that there also exists reflection coefficients and transmission coefficients that some people use for power. Okay. So, field and power are usually two things that physicists and electricians deal with. So, one needs to make sure that there is a clear distinction between the two, right. So, here I am talking about the field reflection coefficient. We will talk about power reflection coefficient as we conclude this section of the course, right. Okay. And then a few more definitions. So, I will say Exi divided by Hyi, right. So, looking from equations, the transformed equations 1 and 2, I can write this as eta 1 cos theta I. Okay, this is for the incident. Okay, so it is simply taking this quantity and dividing by this quantity. Okay, so if I look at the component of the electric field along the boundary and divided by the magnetic field intensity, right, Ex by Hy, it is giving me a certain wave impedance, right. So, we will call this the wave impedance in the z direction. Okay, so for the reflected we have Exr by Hyr, which is minus eta 1 again cos theta r, but since theta r equals theta I, I am invoking that equality and writing this as minus eta 1 cos theta I. This is just to indicate that the wave is traveling in the minus z direction. Similarly, for the transmission, we have ext by hyt is equal to eta 2 cos theta t. Okay, again just simply definitions. Okay, so we'll call this z zi, z z r and z z t. You will soon see why we are doing this. Okay, it is just to simply draw the parallel to transmission lines. If I just look at these components, right, the electric field seems to have component both in x and z, but if I just isolate the component of E along x and look at Ex and Hy, right, I can actually define a wave impedance associated with a plane wave going in the positive z direction, and I am giving them some kind of names, right. So as ZZI, it is the wave impedance of the incident wave in the z direction, right. That is what the subscript Z, I, Z, R, Z, T stand for. So remember, we have one relationship, right. So let me call this 3. This relation 3 comes from, I am going to call these 2 prime and 1 prime. Okay, equation 3 comes from 2 prime, right. And I am going to write 1 prime in terms of these EXIs, EXRs and EXTs, right. Rather than using the magnetic field vector, I am trying to use the electric fields because I am going to define, because I define my reflection coefficients in terms of the electric field intensities, right. So remember, 1 prime is H0, right, which is HYI, okay, can also be written as EXI by eta 1 cos theta I or ZZI, right. Eta 1 cos theta I is simply Z of Zi. Okay, so similarly H0R, I am writing that as HYR, which is EXR divided by so remember ZZR is minus eta 1 cos theta I, so I have to have a minus sign. Okay, so HYR is EXR by minus eta 1 cos theta I, okay, and ZCR is minus eta 1 cos theta I, but H0R is positive, right. So EXR is negative and ZZR is also negative. Oh, sorry. So I think EXR is negative, ZZR is negative. So I don't need a negative sign here. Instead, okay, this should be fine because EXR by ZZR is the definition for HYR. But I think when I write this in terms of ZZI, okay, remember ZZR is minus of ZZI. Okay, so similarly we can write h0t is hyt, which is ext by zz. Okay, so I'm going to transform 1 prime, right? So 1 prime becomes exi by zzi minus exr by zcr is equal to ext by z, oh sorry, this is not zcr, zci and zzt. Okay, again remember the unknowns here are exr and ext. Okay, those are your unknowns. Theta I, theta t are knowns, which means the z, zi and zcr, zzt are all knowns. Okay, the known quantities are all the z's, right? All the wave impedances are known. Exi is also known, right? But exr and ext are the unknowns, right? So I have just transformed my 1 prime and 2 prime equations, which were in the variable h0r and h0t, to exr and ext. That's all I have done. Okay, but there's a reason I have done this. Okay, so we'll come to know very shortly. So let's write these exr by exi as gamma, right? And we'll transform 3 and 4. So equation 3 becomes 1 plus gamma is equal to t. Okay, you can check that. It's 1 plus exr by exi, which is gamma, equals ext by exi. Okay. Similarly, 4 also we can divide by exi, right? In fact, we can multiply by zzi divided by exi, right? So equation 4 multiplied by zzi by exi gives you 1 plus gamma, right? Because zci is cancel off there. Actually it is minus sign, right? We had a minus in the equation. So I have t on the right hand side multiplied by zzi by zzt. Okay, so please check my math. I am following my notes here, but nevertheless I think it's important that you also ensure that you keep me right in terms of the positives and negatives, right? There may be always small blemishes in terms of signs or say subscripts and things like that. Okay, so now let us solve these two simultaneously. So if I can just add these two equations, I get 2 equals capital T into 1 plus zzi by zzt, which implies my transmission coefficient is 2 zzt by zci plus zzt. and if I substitute this in equation 1, I get gamma is equal to t minus 1, which is 2zzt by zzi plus zzt minus 1, which gives me zzt minus zzi by zzt plus zzi. Okay, hopefully the mystery is now lifted. The reason to come up with all these complicated wave impedances in the z direction and so on is all to essentially come up with this simple looking expressions that look awfully like the ones we derived for transmission lines, right? So the reflection coefficient, the field reflection coefficient gamma looks very similar to the coefficient that you get for a reflection of a complex load ZZT connected to a transmission line with a characteristic impedance of ZZI, right? Quite fascinating. Okay, it should all kind of tell you that the underlying mysteries of what is operating these behaviors in the transmission line is fundamentally through the fields, right, the electric and magnetic fields, because it is no stroke of luck or coincidence that these relationships are popping up every time, right, because they are all mediated by the same fundamental Maxwell's laws, right. So now let us write this out in terms of eta and thetas, right. So gamma, remember ZZT was eta 2 cos theta t minus eta 1 cos theta I eta 2 cos theta t plus eta 1 cos theta I. Okay, so this is my first Fresnel equation, right. Okay, so for a very specific kind of polarization, right, a linear polarization where the magnetic field is parallel to the plane, right, the boundary or the plane of the interface between dielectric 1 and 2 yields me a certain reflection coefficient, right. So remember that we have actually solved that algebraic equation, right. We initially had unknowns H0r and H0t. Rather than solving for H0r and H0t directly by just taking those two equations and solving for them, just sort of rearranging them with new characters gamma t and zzi and zzt, we find that we are actually able to see the same sort of equations that we get for transmission lines. Okay, that's the only reason to do 2 slides worth of mathematics, right. But you should be convinced at this point that we have actually completely solved the plane wave reflection and refraction problem at the boundary. We started off by listing down what were the unknowns, which was H0r, H0t and theta I and theta t. The Snell's law relations from the phase matching condition solved for the angles, right. And now through gamma and t, which are the field reflection and field transmission coefficients, we are actually able to also calculate the amount of reflection and amount of transmission, right. So this is something, this should be new to you, something that you have not covered in your high school, right. You are actually in the ability to say, given an arbitrary choice of 2 media and electromagnetic waves incident from one direction, you should be able to calculate how much is reflected and how much is refracted. Okay. Because remember, gamma is essentially EXR by EXI, okay, EXR being the unknown, and EXR gives you H0R, right. So, we are just essentially solving for those, and the right hand side you should be convinced is all known quantities. Theta I, theta t, eta 1, eta 2 are all known quantities, right. Theta t comes from your Snell's relation. So, let us also write the expression for t, which is 2 times eta 2 cos theta t divided by eta 2 cos theta t plus eta 1 cos theta I. Okay. So, this is my second Fresnel equation. Okay. So, we will have 2 more such relations for the next case, which is the perpendicular polarization, okay, where the electric field now is perpendicular and the magnetic field is in the plane of incidence. Okay.